Hi everyone, my name is Idan Arbiv, and I'm excited to present a work on sequential disentanglement by extracting static information from a single sequence element, which will be presented as a poster at ICML 2024. This research was conducted in collaboration with Nimrod Berman, Ilan Naiman, Gal Fadlon, and Omri Eisenkot. Today, I will discuss a novel approach to unsupervised sequential disentanglement, which addresses some of the key challenges faced by the current method in this field. Representation learning is a core task in deep learning. A sequence disentanglement is a key aspect of this process. Unsupervised sequential disentanglement seeks to decompose input data into latent factors of variation, distinguishing between static, the time invariant, and the dynamic, the time varying components. For instance, the expression of the character can be viewed as a time variant feature, while the appearance of the character is considered a time invariant feature. One of the challenges is mode collapse. Current approaches to sequential disentanglement rely heavily on conditioning both static and dynamic factors on the entire input sequence. This can result in information leakage, where static information is captured by dynamic components or vice versa. To mitigate this, some methods reduce the dimensionality of dynamic vectors or introduce mutual information loss terms. However, these approaches come with their own set of limitations. Hyperparameter tuning. Hyperparameter tuning is crucial for optimizing model performance, but can be highly challenging due to the complex interactions between different parameters. Existing methods often requires extensive tuning to achieve a balance between static and dynamic information, making the process time-consuming. Domain-dependent data augmentation. Many existing methods use terms like mutual information, which requires positive and negative examples, thus requiring data augmentation. The challenge lies in designing augmentation that are suitable for both static and dynamics aspects of the data without introducing biases that could affect disentanglement quality. Producing this augmentation is not only difficult, but also increases model complexity and time-consuming. In contrast, a model that does not rely on mutual information terms at all simplifies the model and reducing the need of extensive data augmentation. We propose a novel and simple architecture that mitigates information leakage by conditioning the static posterior on a single sample from the sequence. This is based on the assumption that the static factor, being time invariant, can be extracted from any single element in the sequence. Our framework eliminates the need for mutual information loss and does not impose constraints on the dimensionality of the factors, resulting in a much simpler and more effective model. We adopt VAE modeling and assume the following Joe distribution, where the dynamic and the static factors are assumed to be independent. Each xi depends only on the static factor S and the dynamic factor dt. The posterior distribution disentangled the static and dynamic factors, and it is approximated by Q. Here, S is conditioned only on one element of the sequence, and dt depends on the dynamics of the previous time step and the input until the current time step. The loss function takes the following form. The first term is the summation of both reconstruction term of the first element of the sequence, which is dependent on S and D1. Note, we choose here xi to be equal to x1, but alternatively, we could choose any other sequence element. The second term in the summation is the reconstruction term of the rest of the sequence dependent of S and the corresponding dt's. The next part of our loss is the KL divergent between the posterior of each factor and its prior. The overall loss aims to maximize the reconstruction and to minimize the LS divergent term. Our sequential disentanglement model processes the input sequence x1 to t to output its reconstruction by passing through a problem-dependent encoder that yields an intermediate sequence representation G1 to GT. Each element, xt, is processed independently. The sequence G1 to GT is split into G1, or any GI, and G2 to GT, which follows two distinct paths. To extract static information, G1 is fed into MLP layer to produce a latent variable S tilde. From S tilde, two layers learn the mean and the variance, allowing sampling the static factor S via reparameterization trick. For dynamic information, G1 tilde is sampled from normal distribution, and G2 until GT is fed into an LSTM model which processes the sequence while mitigating static information leakage by subtracting G1 from G2 to GT. The LSTM hidden state, H1 to T, are used to compute the mean and the variance, from which the dynamic factors D1 to DT are sampled. Finally, the static and the dynamic factors S and DT are combined and passes a domain-dependent decoder to reconstruct XT. The provided figure illustrated this flow, showing the sequence processing, splitting, static and dynamic factor extraction, and final reconstruction. To evaluate our method, we use the sequential disentanglement benchmark and show state-of-the-art results in most of the datasets and data modalities. In our image benchmark, our model shows superior performance in generating high-quality image with clear disentanglement of static and dynamic components. For audio data, our approach shows competitive results in static EER and state-of-the-art results in dynamic EER, and eventually in the disentanglement gap. In the time series prediction, our model demonstrates significant improvement in forecasting accuracy. By efficiently disentangling the static and dynamic factors, we were able to make more precise prediction, particularly in complex sequence with varying temporal patterns. For time series classification, our model achieved higher classification accuracy by isolating time invariant features, which enhance the model ability to distinguish between different classes based on the underlying static information. Our evaluation framework specifically addressed the information leakage, showing that our method significantly reduced the undesired mixing of static and dynamic information. This leads to more robust and understandable representation. Dynamic generation. Our model distinguishes between the time-varying and the time-invariant components of characters, separating appearance from expression. By freezing the character appearance and generating new dynamic expression learned by the model, we create diverse samples of the same character with varying expressions. Our model allows for swapping the dynamic and static factors between two characters. This functionality enables us to exchange the fixed visual features, static components, while preserving the learned dynamic expression, resulting in new character variation with different static appearance but consistent dynamic expressions. In the mag dynamic T-SNE visualization, our model dynamic representation clearly clustered according to the temporal variation, illustrating the effectiveness of our approach in capturing and disentangling the dynamic factors in the sequential data. Similarly, in the air quality dataset, the static T-SNE visualization showed distinct clustering of static components, demonstrating the model ability to isolate and represent the time-invariant factors accurately. The contribution of our paper is the following: a novel architecture for sequential disentanglement that condition the static posterior on a single sequence element. Our approach supports complex dynamic, mitigate information leakage, and simplifies training, demonstrating superior performance across multiple data modalities, including images, audio, and time series. Our code is available on GitHub, and we look forward to see you at our poster session. Thank you very much for your time.